Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to lecture number 16 on the subject of computer organization and assembly language programming. The title of today's session is Hack Machine Language Part 1. Well, in the previous two lectures we talked about the instruction set architecture in general, and today and in the next few lectures we will talk about the ISA of hack computer. Dear students, remember the hardware design and the machine language design go hand in hand, and you have to know one in order to understand the other. So today we will quickly have a review of hardware of the hack computer, which we have been designing in the previous sessions, and after that we will move on to the software part of this hack computer. We will design the two types of assembly instructions, namely the A instruction and the C instruction. And to have a clear understanding of these two types of assembly instructions, we will take the help of a few examples as well. So we can say that we are going to design the ISA of our hack computer, that is the class of ISA, types and sizes of operands, operations including the control flow instructions, memory addressing models and addressing modes, and of course the encoding scheme of the machine instruction. And this we are going to start today, and inshallah we'll finish in next 2 or 3 sessions. Before I proceed, let me pay my gratitude again to Professor Noam and Shimon, the authors of the book The Elements of Computing System and the designers of the course NAND to Tetris, whose work inspired me to redesign the computer organization course at PUCIT. Okay, we have a lot to do today, so let's start playing. Well, dear students, let us first quickly have a recap of hack computer hardware, most of which we have already designed in form of individual chips, and sometime later we will inshallah integrate all those chips to have a complete hack computer as shown over here. The main components of our hack computer are a CPU having the ALU and a bunch of registers and control unit, 2 separate memories, one for the instruction and one for the data, a keyboard to get runtime input from the user, a screen to display the output of a program, and of course the data path, that is the instruction, data and the address buses. And remember, there are certain hardware components that we still need to design in the later part of this course. Well, dear students, first of all, I need you to remember that a hack computer is a 16-bit machine. A 16-bit computer is a machine in which everything consists of chunks of 16 bits. So if we want to store something, we have to store 16 bits together. If we want to retrieve some piece of data, we have to retrieve 16 bits. And if we want to move data from one place to another, we move them in chunks of 16 bits. Let us talk about its components one by one. First of all, it has a CPU capable of manipulating 16-bit values. It has a data memory called RAM, which is a sequence of 16-bit values having 32768 locations or registers, and of course having an address of 15 bits. The hack computer has a separate instruction memory called ROM, which is also a sequence of 16-bit values having 32768 locations or registers, and of course the address of instruction memory is also of 15 bits. It has 2 memory mapped I/O devices, a screen and a keyboard. And finally we are going to have all sort of buses that enable us to move data from one place to the other. The instruction bus moves instruction from instruction memory to the CPU. The data bus moves data in and out of data memory. And there are address buses as well, which are not shown in this figure right now. Dear students, we will be designing all these buses when we will design the data path of our hack computer in some future session, inshallah. So, after having a bird's eye view of the hardware, let us talk about the software as well. The software of our hack computer. Dear students, it is the software which is going to control this computer. And at this level, the softwares are the programs that we will be writing in assembly or the machine language. Well, the hack machine language consists of just two types of instructions, 16-bit A instructions or 16-bit C instructions. And a hack program is a sequence of instructions written in the hack machine language. Now $100 question is how to tell this hack computer to run a program. Well, we write a program in hack machine language and each instruction will be a bunch of 16-bit values. Somehow we will load this program inside the ROM. We will then press this reset button and the program will start running. Now what the program will do actually depends on the machine instructions that we have written inside the program. It can be a music player, or maybe a program showing a video clip, or maybe computing the average of a million numbers, maybe a ping pong or a Tetris game. And before we go on to talk about the machine language, let me say a few words about some more hardware artifacts that we have to be aware of. Well, this hack computer has three registers. First of all, there is a D register, D for data, which is used to temporarily hold a 16-bit data value. Then there is an A register, A for address, which can hold an address of memory and can also hold data if required. And then there is an M register, M for memory, which is the selected memory register. Remember, at any given point of time, only one memory location, which is the selected memory register, is pointed to by this M register. Well, now I think we have all the basic background that we need to understand the syntax of machine language. So let me move forward and let me talk about the A instruction first. Well, dear students, an A instruction is used to set the A register to a 15-bit value. The assembly syntax is @sign value, where value can be a non-negative decimal constant ranging from 2 raised to power 15 minus 1, or it can be a symbol to such a constant. Well, the semantics are this A instruction @value will set the A register to this value, and after this the RAM of this address becomes the selected RAM register, as well as the ROM of this address becomes the selected ROM register. For example, @17 actually sets the A register to a value of 17, and as a side effect, the RAM location 17 becomes the selected RAM register, so we can read it and write it using some other instruction. So let me move on to the second type of instruction, the C instruction. The syntax of this instruction consists of three different fields: the destination, computation, and a jump directive. Now $100 question is how does it work? First of all, the computation is done, and after that we can do one of two things. We can either store the result of the computation in some destination, and in that case the syntax of the C instruction will be destination is equal to computation, or based on the result of computation we can decide if we want to jump to some other instruction in the program, and in that case the syntax will be jump to computation. So let me move on to the second type of instruction, the C instruction. The syntax of this instruction consists of three different fields: the destination, computation, and a jump directive. Now $100 question is how does it work? First of all, the computation is done, and after that we can do one of two things. We can either store the result of the computation in some destination, and in that case the syntax will be computation semicolon jump. Now let me go into a bit of more details about every one of these fields. Well, dear students, first of all, let me talk about the computation. Computation can be any one of these 28 different operations. We can straight away place a 0, 1 or -1 as the result of computation, or the values of D, A and M register, or we can do a bitwise NOT of these registers. We can do a decrement or increment to these registers, can perform add, subtract bitwise and bitwise OR on the contents of D, M and A registers. So as far as the computation is concerned, over here you can place any one of these symbols or operations. Next is the destination. Well, we can have these 8 possible destinations. Null means that we don't want to store the result of our computation. And we can store the result of the computation in either the M, D or A register. We can store the computation result in any 2 of the registers, or maybe in all of the 3 registers. Let's talk about the jump directive as well. Well, the jump directive can also take these different values, these 8 different values. This null means we don't want to jump, and this JMP jump means an unconditional jump. And the rest of the 6 symbols are used for conditional jumps. For example, JGT means jump if result of computation is greater than 0. JEQ means jump if the result of computation is equal to 0. JGE means jump if the result of the computation is greater than or equal to 0, and so on. So to cut it short, the computation result is always compared with 0 in case of the conditional jumps. And here is the working. A C instruction can be used in either of the following 2 ways. The first is destination is equal to computation. That is, you want to store the result of a computation at some destination, then you use the C instruction, something like this. And in this case, note that this semicolon and jump directive are omitted. The other use is you use the result of the computation to make a decision to jump. And in this case, you can notice that this destination and this is equal to sign are omitted. Well, dear students, let me go through a series of examples in which I will be using both these instructions to have a clear understanding. And here is the syntax of A instruction for your ease, and here is the syntax of the C instruction. And let's suppose that there is a programmer who wants to set the register D to a value of -1. So this can be done using the C instruction, using destination is equal to computation syntax. So in this case, since the destination is D, so over here we will have D, and the computation is of course -1. So the destination is D, the computation is -1, and the syntax will be something like this. So this is the hack assembly A instruction that sets the register D to a value of -1. Let's see another example. Suppose the programmer wants to increment the value of D. So if a programmer wants to increment the value of D, once again we have to use the C instruction. Destination is equal to computation, and in this case the destination is of course D and the computation is D plus 1 because we want to increment the value of D. And the exact C instruction that will perform this task is D is equal to D plus 1. Let's see another example in which the programmer wants to add the contents of D and A register and place the result inside the D register. Once again, the C instruction is used for this. The destination is D because we want to place the result in D register, and the computation is D plus A because we want to add the contents of D and A register, and the exact syntax is D is equal to D plus A. I hope this is making sense to you. Let's see another example. Suppose the programmer wants to store a number 10 in D register. So the destination is D register and the computation is 10. We don't have any computation which is a 10 that can be stored inside this D register. So this task cannot be performed in one instruction. So we have to use the A instruction first to set the stage for our subsequent C instruction. So the A instruction can be used to place a value 10 inside the A register. So this is the syntax of A instruction, that is placing a value of 10 inside A register. Now we can use the C instruction to perform the task, in which the destination is D and the computation is A, and A already contains 10. So these are the two instructions which will together perform the task of storing a number 10 in register D. Suppose the programmer wants to write the value of register D at RAM 135. That is, you want to write the data memory, and the address of the data memory is 135, and what we want to write at this location of RAM is the content of D register. And what are the contents of D registers? That is whatever we have computed in the previous instructions. So this again can't be done in one instruction. First of all, we'll place this address 135 inside the A register using the A instruction. And now, since A contains 135, the RAM register at address 135 is the active register. The final task can be performed using the C instructions, in which the destination is of course M, the register M, which is actually pointing to RAM address 135, and the computation is D. So these are the two instructions that are going to perform this task. Dear students, please do not worry much. We will do a lot of practice of these instructions, and later on you will have a mastery of this, and you will be able to write a reasonable level of assembly programs in the hack assembly language. Okay, so in this example, the programmer wants to write the value of register D with an increment at RAM address 135. This is again very simple. We first need to set the A register, the address register, to 135, and now the M register is actually pointing to this location, and this can be done something like this. The destination is M and the computation is D plus 1. So in this example, we have written D plus 1 inside the memory at address 135. Suppose the programmer wants to read the memory now. In the previous example, we have written the memory, and now we want to read the memory. And from which location? From address 325. And we want to read the contents of RAM at address 325 and want to place it inside the D register. And for here again, we have first of all need to place the address of the RAM where we want to read inside the A register using the A instruction add 3 to 5, and then we are going to use the C instruction and over here the destination will of course be the D register, and the computation is M. So this is how you are going to read the contents of memory location 3 to 5 and place them in D register for later computation. Okay, now let's suppose that the programmer wants to do an unconditional jump. Suppose in the sequence of the program we just want that the control of execution should be shifted to the ROM location 431. And for this as well, first of all, we need to use the A instruction, and we need to place the address 431 inside A. And now, as I've said in the previous slides as well, the RAM as well as the ROM, both locations 431 are active now. And now I'm going to use the C instruction, and this time you see I have not used the destination and is equal to sign. I have just used the computation semicolon jump portion. Inside the computation I'm going to place a 0, because in case of unconditional jump the computation should be 0, and the directive is JMP, unconditionally jump to this address. So these are the two instructions that we can use to unconditionally jump to this address. And whatever address is written over here, your program control will move on to the instruction located at this address. And let's suppose see the example of a conditional jump now. And the condition is if D minus 1 equals 0, the control of execution should move to instruction located at address 97 inside the ROM. So over here as well, first of all, we need to place the address 97 inside the A register using the A instruction, and then we are going to use the C instruction, this portion of the C instruction, computation semicolon jump, and the computation is of course D minus 1, and the jump directive that we are going to use is JEQ, because the condition is if D minus 1 double equals 0, only then we should jump. We can use any other jump directive over here as well. So these are the two instructions which will move the control of execution to ROM address 97. Okay dear students, suppose that the programmer now wants to write a constant 54 at RAM location 17. Please pause the video for a minute or so, think it out, see the previous slides, see your notes, and see if you can do it. And meanwhile I'm moving ahead. Well dear students, this cannot be done using two instructions, because first of all we need to place this constant 54 inside the D register, and then we need to use the C instruction for this part as well, that is writing of the RAM. So again pause this video and try to writing the A and the C instruction that can perform this task, and the A and the C instruction that can perform this part. Meanwhile I am moving ahead. First of all, D is equal to 54. This can be performed using these two instructions. We have placed a constant inside the A register using the A instruction, and then we have used the C instruction in which the destination is D and the computation is A. And to write the memory location, once again we need to place the address 17 inside the A register using the A instruction, and then we have used the C instruction that performed this task. Well, this example shows you that the A register can be used for data, as you can see in this example, and the A register can be used to place the address of the RAM or the ROM as shown in this example. My dear students, I will strongly recommend that you do these examples at your own. Think of some more examples, practice it so that the concept of using A instruction and C instruction should be very clear to you. Okay, so that is it. Today I have tried to give you an overall description of the two types of instructions of hack computer language. We have discussed the symbolic flavor of the language, and in the next lecture inshallah we will see how can we write or transform these symbolic instructions to binary codes or machine instructions. I strongly recommend that you should re-listen to this video. You should practice these instructions using a copy and pencil before going with the next lecture. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.